Okay, everyone, in this video, we're going back to confidence intervals. The difference this time is we won't be doing confidence intervals for a sample proportion, but rather we're going to create them for a sample mean. The biggest and most important thing you're going to get out of this video is that we're finally going to be using a different curve to approximate these p-values. Instead of using the normal curve, we're going to use something called a t-curve. So you have to watch and listen to the video carefully so you understand when to use a t-curve, why we use it, and how we're going to use it, how it's different than using a normal curve. So I don't know if you guys remember Mr. Valentine. He left after last year, but let's just say he wanted to estimate the average weight of an Oreo cookie. So Nabisco says they are 11.3 grams, but he thought maybe it was less than advertised. So we could run a significance test with this, where the alternative would be that the average weight of an Oreo cookie is less than 11.3. But today, like I said, we're going back to confidence intervals. So instead of running a significance test, we're just going to create a confidence interval for plausible weights of these Oreo cookies, and we'll see if 11.3 is contained in there. So this is what your paper should look like so far. We still have a lot of the same terminology. We have a point estimate. That's going to be given to you in the word problem. I guess our population is just all Oreo cookies. What we're looking for is the true mean weight of all Oreos. Look at this X bar again for the statistic. You're kind of used to using p hat because we've been doing proportions, but today it's X bar because we're going back to sample means. And Mr. Valentine took a sample of 30 Oreos. So it was random. It's important. We talked about this a couple weeks ago for these two reasons. The biggest is number 2, to generalize our findings to all Oreos. But a lot of you like to give me number 1 as well, which is true. We want to make sure that our sample isn't biased, and then therefore our confidence interval would be very biased. So maybe add on your notes that this is, again, just the first condition we're going to want to check for random. You're used to that. That shouldn't be anything new. Okay, now we really got to go blast from the past. I put this up on the board for you, but reminding you of this formula, it's totally different than the square root of p times 1 minus p divided by n. This is what we used the lower half of your formula sheet when we were solving for problems dealing with means. So when we go to use this problem, something very unique happens. We have our sample size, obviously, but we have no idea what the standard deviation of the population is. Let's see if I can type that in here. Oh, I can. Okay, maybe I can't. Well, I'm not sure why this is. Sorry, I'm just curious if I can get it. Okay, we're getting out of that. And I don't like this at all. Okay, sorry about that. If you can write down yourself that this is the standard deviation of the population. I am having a really hard time with this, so take your time. Of population. We don't have that. We're never going to have that. Why would we know the standard deviation of all Oreo cookie weights, but not know the actual weight? So if we don't know that, we are stuck. We can't use this formula. So again, we're going to have to approximate it with this up here. The standard deviation just from Mr. Valentine's sample. So hang tight. Let me scroll down and we'll come back to the 10% condition. So if you see down here, we're using the sample standard deviation. I switched out the notation instead of the population standard deviation, and that's going to cause us some problems. So again, before we can even begin to use this formula, we have to check the 10% condition. Let's jot down that's condition 2. You guys are used to that. But when you are creating a confidence interval or significance test for means, and you use the standard deviation from your sample, instead of the standard deviation from the population, because we just don't know it. Looking at using this over and over again in repeated samples, statisticians realized that the resulting sampling distribution we want to be normal, just like in last chapter, wasn't quite normal. Let me pull up what it looks like. So in red is a normal curve. In blue is what these statisticians saw. By using the standard deviation from the sample in repeated samples, we had too much variation in the tails. Look at blue. There's so much extra variation in these tails. So that's why the peak is lower. It's just not quite normal. So the area that's under this kind of center part is much less than the area under a normal curve, let's say within 1 standard deviation. Look, within 3 standard deviations of the mean, this red curve, my normal curve, is pretty much done. But this blue curve has so much extra area, even 4, 5 standard deviations away from the mean. So this was causing too many problems when they ran a significance test or created a confidence interval with the normal curve. The results were just inaccurate. So they discovered this, and for whatever reason, they decided to call it just a simple t-curve. But I want to show you what happens to the t-curve as sample size increases. You guys know bigger samples are always better, but let's watch. Right now the sample size is only 2. Let's watch what happens to this t-curve in blue as I increase the sample size. 3, 4, 5, 6. Watch what's happening to the blue curve. By the time we get to a sample of around 30, it looks almost identical to the normal curve. So we're still, just like you did a couple chapters ago, we're still going to be looking for a sample of at least 30. And in that case, we'll be able to kind of carry on the rest of our problem. So even though it approaches a normal curve, oftentimes, to be more precise, we still like to use the t-curve just to avoid any complications down the road. I know it's close to a normal curve, but if you're working on a problem with means, for the rest of the year, you should probably just default to using the t-distribution, the t-curve instead, to be more precise. It gets close to normal. It's never quite perfect, so we'll just use the t-curve to get as accurate as possible. So would it be appropriate to use the normal distribution? The central limit theorem says yes. However, when finding the margin of error, blah, blah, blah. Basically, what I'm saying is when finding this standard error and we use the sample standard deviation, we're estimating now with so much variation that we have a totally new curve. So I would try your best to draw. You can see in purple, I have my best drawing of a normal curve. And in green, I have a t-curve where there's more area in the tails and a lower peak. So the t-curve, jot down, has more area in the tails. You can also say it has a lower peak. You probably want to pause the video and jot this all down for a minute. Okay, now that we know we're using a t-curve, let's just go back and talk about our confidence interval formula. So on your formula sheet, let me pull that up. Remember it says this right here. To get our confidence interval, we need our statistic, that's just our point estimate, plus or minus this margin of error, which is our standard error. We just used the formula from right here. Here it is. The standard deviation of the sample divided by the square root of the sample size. And then we need this critical value. So what you were used to doing is getting a critical z-score, which would be from inverse normal. We get these letters z. But now that we're using a t-curve, we're not going to use a z-score anymore. We're going to look for a t-score. We're going to look for the critical value from a t-distribution. So we're going to do that the same way that we found a z-score, kind of using inverse normal, but we're going to go to inverse t this time. So this is the best online calculator I could find. Just ignore this random algebra 2 question in the background. But let me get out of here so you guys can go back to, with your calculators, second vars. So grab your calculators and click back to second vars. You're very familiar with this. But if you notice, instead of inverse norm in number 4, we have inverse t. So go ahead and click on that. It asks you for the area, just as it did with inverse normal. But this time it asks you for df. That stands for degrees of freedom. Degrees of freedom is a very interesting conversation that you just don't really need to have right now. To get a 5 on the AP exam, all you need to know about these degrees of freedom is that they're just one less than the sample size. So if your sample is size 50, your degree of freedom will be size 49. So we'll add that to our notes. Let me pause and go back to those for a minute. So what critical value t-score is needed for this confidence interval? Use inverse t and degrees of freedom n minus 1. So if we go back up, our sample was size 30, so we're going to use 29. And remember, we had to kind of find the area in the left tail. All of us are going to need to do that again here. So if you were not used to doing this with inverse normal, unfortunately, it's the only way to use inverse t. So you're going to get accustomed to it now regardless. So since we wanted to create a 95% confidence interval right here, we're going to do 1 minus 95%, which is 5%. Divide that by 2, we get 2.5%. Convert that to a decimal, 0.025. And the degree of freedom will just be 29. So let me show you what that looks like. You can follow along. 0.025 is the area. Notice it doesn't give you the option for a tail, left, center, right. Let me make sure. I'm grabbing one of our school calculators. Yep, nope, it doesn't. So we're all stuck doing it the long way. Degree of freedom is 29. And in this case, our t-score is negative 2.04. So let's go back here. It gave me negative, but remember, we're looking for how many standard deviations away we need to travel. So we're just going to always use the positive version. So I just made it positive. So see if you can take this, multiply it by the standard error we calculated back in number 5 to get our margin of error, and then use the formula. Oops, sorry. Where did that formula sheet go? Oh, there it is. Use this formula. So this is the result Mr. Valentine got from our sample, plus or minus that margin of error, to see if you can finish this confidence interval, and we'll check it together. So you should be working on, oops, I just gave you the answer. Okay, well, you should be working on number 9 and 10. Try to finish by interpreting in number 11, and I just wanted to say that I'm going to post this link in Schoology if you want to play around with the t distribution versus the normal distribution as well.